Hi, today's video is all about mazes. Mazes written in BASIC and mazes written in C programming language. Real mazes and some maze art, and all of that on Commodore 64. Now, I'm not talking about 10-print maze here, I'm talking about real mazes like this one that you see behind me on the screen. Well, this in fact is not my maze. This maze was made by Back to Basic channel, and his video actually inspired me to look a little bit more into this topic and show you some algorithms and methods that we can use to create mazes on Commodore 64. So big shout out to Back to Basic channel. This is not the first time that his video inspired me to do something similar myself. He does some great stuff in Commodore Basic, some games and programs, so I highly recommend that you check out this channel. Now, before we jump into the code, I would like to show you a small demo I made of all different mazes that we are going to explore in this video. So let's start with that. And just a little bit more before I actually show you the code, or to be precise, the codes. I want to talk about these algorithms, and in today's video we're going to use two types of algorithms to generate mazes, and I want to explain how each of these works. So the first one is called Recursive Backtracker, and it's very commonly used algorithm to generate mazes because it's very simple to implement. It's a bit slow, but on the other side, it's very interesting to look how this algorithm works and generate maze. So yeah, there are pluses and minuses. So the other algorithm is called Recursive Division, and it's completely different type of algorithm. It's very fast, it's not so interactive, it's not so interesting to look at. But it's very clever way to generate mazes, and you probably noticed that couple of mazes by the end of that small demo of mine. There are a couple of mazes that looks completely different from all the others, and those mazes were generated using that recursive division algorithm, and it's very nice algorithm indeed. So yeah, but let's start with this recursive backtracker. To implement this recursive backtracker, and it's called backtracker because we are using a stack to stack all the positions that we use in our current path, because using this algorithm we generate path and everything else should represent walls. So we use a stack, and it's called backtracker because we are going back through the stack, and we're pushing positions on the stack and popping position from the stack, and so on and so on. as you will see very shortly. So let me just write here, this will be our stack here, just a representation of stack. We call it a stack, but in fact you will see in my programs it's just array. Nothing really special about that array of positions. So okay, let's go with, I'll use invert space, that's the most common one. So let's start at some random position, let's say here, and we have to store this position onto our stack. So we have to store every position wherever we go, whenever we create a path, we have to store all of those positions onto our stack. And we choose randomly to go left, right, up and down, okay, so everywhere where we can. So let's say that we decide to go right, and then again we have to store that position as well on the stack, and then we choose to go right again, and then we go up and more up, and then let's go left again, then let's go up, and everywhere as we create a path we need to store every position from that current path onto a stack. That's very simple. So let's create some more positions, and let's go here, and then let's go here and store this position onto our stack, and now to go right here, let's say, and now we reach the dead end. So did I mark that position onto a stack? I believe I didn't. Okay, so now I did. So this is our dead end, and I will color it red. So from this position there is no available directions to go to, we cannot move anywhere. So the beauty of this algorithm is this. Now we go back through our stack, so we are popping elements and we are searching the closest element which has some available new direction to take. We leave this position on the screen as it is, we remove it from the stack, and we progress backwards through the stack, so we are popping elements. So we are checking this previous position or the current position on our stack, and that's this position right here. I will color it red. Okay, now this position here has one available direction, that's up. Our current path is now going to the up, and here it is, and we store that position onto our stack. Now again we reach the dead end. In that case, this is the dead end. Again we repeat the whole process going backwards through the stack. So that means that we leave this position on the screen, we remove it from the stack, and we are checking this position now, and which is again this yellow position here, and again we are checking is there any available directions to go to from that position, and there isn't. So again we remove this position as well from the stack. Now the next position is this one, and I will color it yellow here. Now this position has some available free directions to go to, so we randomly choose to go left or down. So let's go and choose left, and we continue to fill our stack, and this is how this algorithm works. Eventually, if we let this algorithm run long enough, it should fill entire screen with characters. So we should go through every possible position on the screen, and the beauty of this is we actually know without checking, without peeking, is every position on the screen already marked or not. We know when we are done, when we complete the entire area that we want to fill with characters, once our stack is back to 0. Once that happens, we know for sure that we filled entire area with characters or entire screen, whatever you want to use. But as you can notice here, this doesn't really look like a maze at all. This would be actually very slow and very inefficient way to fill the entire screen with characters, but it's very good to create mazes. We just need to add a bit more rules, so let me show you that. Let me delete all of this and let me delete our stack and start all over again. So we are starting again at some random position. The new rule that we're going to implement or apply on this algorithm is that we can change directions every 2 steps or on even positions when we have even x and y coordinates. Now what will that give us is this. We start here, and if we decide to go right, we have to go we need to store this position as well on the stack. If we decide to go right, we have to take 2 places, so we have to make 2 moves to the right, not just 1. And again, we store these 2 new positions onto our stack. Then we decide to go, let's say, up. Then we have to take 2 positions, 2 steps to the up. Again, store these values as well. And then we decide to go left. Again, store these positions onto our stack. Now, obviously, we cannot go downwards, so that means we cannot go down, because taking 2 positions, taking 2 steps would collide with this position that has been already taken. So that means we can go either left or we can go up. So let's go up and so on, store these positions and so on and so on. Let's go, oops, sorry. So these 1, 2, 3, 4. So as you can see, this already looks like a maze. And like I mentioned before, using this algorithm, we create a path, and everything around us should represent a wall or walls. So that's it. This is how the maze is created. Now, the second problem here is how do we know which directions are free to take and which are already taken. So where can we actually move? Because we're constantly using a random function to choose between directions going up and down, left and right. So how do we know which directions are taken or not? So there are several ways to do this as well. There is not just one solution. And I will show you the solution that I implemented, that I used. Let's say that we are currently at this position. So obviously, by looking at this position, we know that we cannot go backwards. So that's one direction already taken. We cannot go right because we would collide with this position right here. The only possible option is to go continue to go downwards or take a left. Now you can achieve this by picking those positions and detecting whether or not those positions are free, but this is very time-consuming process, and doing this in BASIC would take a lot of time. So instead, what you can do, and what I have done, is I created a lookup table. And so lookup table for directions. Okay, so I created a lookup table for directions, and again, this is just array. It can be 2-dimensional array with x and y coordinates. It can be single-dimensional array with just absolute positions of element on the screen. So it doesn't have to be 2-dimensional array. It doesn't really matter. It doesn't change the concept. So for every position on the screen, I use single byte to define which directions are free and which are already taken, and I kindly borrowed the concept from the joystick registers. So I use simply 4 less significant bits in the byte, or to be precise, a nibble, to define which direction is already been taken and which one is free. The taken directions are marked with 1, and free directions are marked with 0. So what that means? Well, let's say that we have our position here, and what I've done is I choose to mark this up position going up with a 1. If we write binary representation of this number, it would be 0, 0, 0, 1. Then I defined this left direction as number 2, which in binary is 0, 0, 1, 0. And then again we have directions to the down defined as decimal number 4. So that's 0, 1, 0, 0. And you can assume that this is number 8, which is 1, 0, 0, 0. And using this method, I can use only 4 significant bits in a byte. Well, in fact, as a matter of fact, I have to use the entire byte to store all possible combination for all of these 4 directions. So let's say for this example, because we came from going down, that means that opposite direction of that is going up, is already taken for this position marked with yellow. So that means that, let's start with all 4 zeros. Okay, so that means that this position going up is not possible anymore, so this will be 1. Also, going to the left is available and free, so that means that this will remain 0. Going down is available, so this position will remain 0. And this position here will become 1 because we cannot go to the right, it's already taken. I know when I reach this position here, I just look in directions array and find out which directions are available, and then I randomly choose between those directions. So of course this 1001 is actually number 9 decimal, so in this array for this position on the screen I would have number 9 here. So very simple. And then when I choose my next direction, I will mark that as well for this position. So if I choose to go to the left, oops, if I choose to go to the left for this position here, I will change this number, this bit, from 0 to 1, and now the value for this position is not going to be 9, it's going to be 11. So that means here we will change this to 11. So that's basically it. If I want to find out which directions are actually available, I just need to invert this number. So instead of 1011, I will get 0100, and all I need to do is convert this number into specific decimal representation of specific bit position, and I will get numbers that I show here, and that's 1, 2, 4, or 8. So this second algorithm is completely different. So in this first algorithm we are moving across the screen and we are creating a path. On this second algorithm we don't create a path, we don't actually know the path. We create openings in already existing fully closed maze. So what we need here is to show you this, I will first fill the entire screen with a grid, and I will use this character and I will fill entire screen with this character. Okay, so we are starting with this. We choose random position on the screen. So okay, let's start with this random position. So what we do here is we decide whether are we going to split this screen, this whole area, horizontally or vertically. So if we choose to split it, let's say horizontally, so this is how we would split it right here. I need this, and we create opening at this random position. So we can choose here whether are we going to remove this bottom wall or the right wall or both of these walls. So let's say that we clear this, and I need to choose this. So we create opening here. We now have two areas, this upper area here and this down area right here, and we continue this repeat this process for each of these areas. So you can imagine that this is all about recursion. For every area that we split in half, we get two additional areas to work with. That grows exponentially. So let me show you a couple more steps and you will see how that actually works. So for this upper area, let's decide to choose let's say this position here, and of course we will color this right here, and we will create opening right here. Also we have to create a random position right here, so let's choose something like this. Oh bloody hell, where did I lost my... Okay, and then we will split that vertically. So there is one rule which says that depending how our area is oriented, we choose to split this vertically or horizontally. So if we have wide area, it's much makes more sense to split it vertically, and vice versa. So this is what I'm doing here. Again, we will remove create opening here, and if we continue splitting or dividing this area every time, we will eventually reach the area that we cannot split anymore, so it will be just single row or single column. In that case, we just create a wall there, and that's basically it. This is how this whole concept works. It's very fast. The mazes look completely different from this first algorithm. Very clever way to create mazes, and you can be sure once you're done there is a solution for that maze 100%. So yeah, let me show you just a little bit more here. Remove this. So you can see you go with smaller and smaller areas until you reach the area that you cannot divide anymore. And that's it. I mean, it's very clever way, because the walls, if you think about it, the walls of the maze are already here in place. We just create openings through which we can move. Okay, so let's go back to our first algorithm and see how is that implemented in BASIC. Okay, so this is our first example in BASIC, and this first example doesn't actually create the maze. This is just implementation of Recursive Backtracker algorithm, and I want to show you how I implemented that in BASIC. So here I initialize that lookup table for directions. As you can see, it's just simple array with 1000 elements that should cover the entire screen. That's 40 columns by 25 rows. Again, here I could use a two-dimensional array with x and y coordinates, or I can use this. It doesn't really change anything, it's just a little bit different implementation, but everything else is just the same. And like I mentioned before, we need stack, and stack is again just a simple array with 1000 elements. It's high probability that we'll never have a stack full completely with 1000 elements. That means that the entire screen will be filled with characters without ever reaching the dead end. But just to be sure, yeah, 1000 elements. And of course we need stack counter just to know where we are. This is where our main program begins. So at the beginning we just initialize x and y coordinates as a random position, choose the random position on the screen, and this first position on the screen we just store it onto our stack and mark it with a poke on the screen, just position to see that element. And then we jump to line 1000. This is our main loop here. So after this loop is done, it's completed, we just stay here waiting for some key to be pressed, so that program doesn't end immediately, so that our maze is visible on the screen without ready prompt. So yeah, and this is our main loop here. There is no really that much code, so we will go through all of this. So our input parameter, and I just say input parameter, but there is no input parameter, but we start with the stack counter. Every time we just work with the last element on the stack. That's it. So whatever is the last element is on the stack, we work with it. First, what we do here is we check whether or not our stack counter is less than 0. That means that our stack is completely empty, and that means that we are done. We fill the entire area with characters. That's it. So in that case we just end this loop and we are going back here waiting for this key to be pressed. That's it. Then if that is not the case, then we are reading that position from the stack and calculate x and y coordinate from that absolute position. And then we are checking in our lookup table for directions whether or not all directions are taken, so there is no free directions to go to, so that means that we reach that end. In that case we are jumping to line 2200, and that line is right down here, and this is like little subroutine for dead end. So what we do here, we decrement the stack counter, of course, and we are removing that. We are popping out that element from array. We cannot pop that really that element from our array. We just define it as we set the value 0 to it. Even that is not really necessary. It's just enough to decrement stack counter. So yeah, and before that I colored this position differently so that we have a little bit of effect on the screen, so that we can see when we are going back through the stack, that's colored a little bit differently on the screen, so that we can see what's actually happening. And after that we are going back to line 2020, and that line is again right here. Again, once we reach that end, we check again, is this the end of our stack? Are we done? If not, we are again on the last element on the stack. So as you can see, we are always working with the last element on the stack. Okay, so in case that this is not true, so we have some available directions. For this example, these two lines are just here to choose random available direction that we will take for our next step. And this works like very simply. We choose randomly between all four directions, and then we check whether or not this direction is actually free or not. If it's not free, then we are just looping over and over again until this random function actually hits the free direction. It's not very efficient way to do it. I will show you two more examples how this can be solved. But for now, let's go with this. And then we have a couple of if statements. Of course, we have to check whether or not, in case that we want to move to the up, whether or not we are hitting the border. So our y coordinate is 0 or our x coordinate is 0. So what we are doing here, if y coordinate is 0 and we want to move up, of course we cannot do that. In that case, we are just marking for that position that direction to the up is taken and it cannot be used, and we are again jumping at line 2020, and that's this line again right here. So in case that this is not true, so I don't need even these. Okay, so in case that is not true, we just decrement y coordinate -1. In case we are going up, in case that we are going left, we decrement x coordinate, and so on and so on. And this a variable is direction for at the moment current position on the stack that we are working on, from which we are going to create our next step. That means that direction for that element is taken in opposite direction. That's just it. And we can speed this a little bit more if I add here, because we don't have, once we decide which direction to take, we just take one direction. We cannot take multiple directions at once. So if we decided to go up, we don't have to check all of these lines, so we can jump directly to this line here. And same goes with this, and here we don't have to do anything to automatically continue on this line. Okay, so that's that part. And now what we do, we just calculate for our new x and y coordinates. We calculate absolute position on the screen. We increment stack counter. We add that new position onto our stack, and we define that this new position has already taken one direction. That's the direction that we came from. So like I mentioned before, if we move to the up, then the opposite direction is already taken. If we move to the left, then the opposite direction that means the right direction is taken, and we mark that immediately here. Then this line here, so we just use poke commands to display that position on the screen. And what I'm doing here again is just, it's not necessary to do it like this. This is just poking our new position with different character, and the old position, the previous position, is will have a little bit different character, so that it's just visual effect on the screen, nothing more. And this part here is where we check all the neighbors for that new position that we just added to our stack. We have to mark all the neighbors of this new position, that some of their direction is now taken. And that's basically it. And now we just go back to line 2020, which is again here. We start all over again. So because we added a new position onto our stack, we are now where am I? We are now working on that position and checking its directions, which are available or not, and so on and so on. And this is our entire code. And here we go. As you can see, just filling the screen with the characters, moving around randomly. And you see this white color character with a white background is just parts where we are going back through our stack and starting all over again. And as you can see, it's quite slow. And eventually we will fill the entire screen with the characters. So yeah, that's about it. Let's end it. And this is our code. Yeah, that's about it. So now we have a couple of problems to solve here. So first of all is this section here, and this is where we randomly select 3 directions to take. So you see, we try to guess, we try to randomly select 3 directions, and every time we need to check whether or not this direction is actually free. If not, we are just looping constantly, and yeah, so here we can lose a lot of time. So instead of doing this, we can use something else. We can use a lookup table and try to and by using a lookup table. So instead of doing this, there is several other approaches. I will show you 2 more solutions. Both of these solutions are implemented through lookup tables again, because that's the fastest way to do this in BASIC. We will use some additional memory, of course, but we should gain some speed here. So yeah, let me show you that. This should be this exactly same code, except we added additional array. This time is 2-dimensional array, and this array is actually for available directions. So what that means? That means for every possible combination of 3 directions, we have in lookup table already prepared array from which we will randomly select one of the direction. Our lookup table, or the values for the lookup table, are stored as data here, and we just read that data and store it into this array. So as you can see, we have numbers from 0 to 15 because these are the numbers for 4 last significant bits. So we go from 0 to 15. And for every of these numbers, we have an array of 5 elements where we defined how many free direction is there available for us and which one they are. So yeah, so let me show you that. And this is now, instead of these 2 lines, now we have 3 lines, but we don't have if statement anymore. So at the beginning we just invert our because in this direction table I actually store not free directions but already taken directions. So if we invert this number, we will get free directions. So this is how what is happening here, and this is the fast way that I know that it can be done in BASIC. We just from number 15 we just subtract our taken directions value for all taken directions, and we will get everything that is free. Okay, so now we just jump into this lookup table, and the first element in that lookup table is so I use this variable a, which actually represents how many free directions is there for that value, and I just simply select randomly between those values. So, and after I do that, I just use that direction. That's it. So let me show you in the easiest thing would be to show you in the last couple of numbers. So this is our number 15, this is 14, and this is 13. And the first number here, like I mentioned before, represent how many available direction is there for that value. So here we have all 4 available directions. When we start, we have a position with none of these none directions are taken, so that means the value is 0. If we invert the 0, we get 15 minus 0, which is 15, and this is it. So we have all 4 directions available, and now we just randomly select number from 1 to 4 and we pick one of these directions. As you can see, they are just decimal representation of for every direction. That's about it, and that's how we select our next move. Of course, here for number 14 we have only 3 available directions, and here they are just this direction. So direction number 1, that for the up, is taken. Well, we have to define the value in the array. We cannot have array with different number of elements in it, so I just store 0, but I don't actually use it. So same goes with our number 13, which again has only 3 available directions to go to choose from, and here they are. So they are now different directions, and so on and so on. And using this method will speed things up. So yeah, so I now just broke my code, but never mind. So that's about it. And there is another way, another type of lookup table that we can use for this application, and let me try to show you that. Here we go. So here we have again lookup table. It's a little bit different than this previous one. We don't use actual numbers, we use strings. And again, you can see the concept is exactly the same. For every number, we have all available directions, this time just stored as a string. So let's say for value 6, we have only available directions 4 and 2. That means that we can go only left and down, and so on and so on. You see, there's some of these have only one available direction, some of them has 3, 2, whatever. And again, this code is a little bit different here, because first, again, we invert our taken directions to 3 directions, so we invert our number, and then we have to select that string from this lookup table. And once we select that string, then we have to calculate the length of the string, right? So we have to know how many characters there is inside that string, and then again we choose random characters or random number, and then we just use this mid function to grab one of these directions and convert it from the string to number. That's it. So again, little bit different approach, works just fine, and it's faster than using that try to guess randomly over and over again one of the 3 directions. Everything else here is the same. Okay, so still I haven't shown you actual maze. We just filled the screen with characters. So let me show you that. So far we haven't actually created any mazes because we were just filling the screen with the characters. And to create maze, not only that we need a path, we also need a walls. And to create this illusion of walls, the easiest approach would be to create space between our path. And we can achieve this by changing directions every 2 steps. So that means that every time that our direction is changed, we have to take 2 steps in the same direction, and then so on and so on. And there are several ways how to achieve this. So you can say that we can change directions on every position which has even x and y coordinates. So we can check those 2 values to see whether or not they are even numbers. We can create a lookup tables with a grid, which will have all positions marked where we can change our direction, so we don't care about anything. We just move and check whether or not it's okay to change direction for this position or not. But also the easiest thing to do is just to follow this stack counter, because this variable will also tell us are we at even position or odd position. So we can use that. And of course you can see here I have additional variable which says previous direction. So every time that we decide not to change direction, then we just use the previous direction instead of it. So you will see that. What we have here is just we are checking that stack counter whether or not is even or odd number. So in this case, if it's odd number, then what we do is we use for this position, we use previous direction. We will not change direction. Of course, we have to close all the directions for this position, and we are just jumping to line 2100. That means that is right here. So we are skipping this part entirely where we randomly select our direction, and that's about it. Everything else stays the same. So let me run this code and show you how this looks like. Everything else is, I believe, oh no, there is some changes, sorry. So this part where we check all the neighbors, now we have to think that our neighbors they are 2 steps away. So that means that these numbers are a little bit different. So instead of going minus and plus 40 for the y coordinate, plus minus 1 for the x coordinate, we have to just double it. So it's plus minus 80 and plus and minus 2. That's about it. Everything else just stays the same. And here we go, a little bit different coloring. But as you can see now, we have space between our path. And now this looks like a maze. Here we go. Let's enjoy this a little bit. Again, this black color represents the points where we go, or positions where we go back through our stack. So we reach that end and we are going back through our stack until we find the closest position that has some available directions to go to. Almost done. And here we go. Our maze is complete. It's done. So I want to show you this example as well. So this is not actually the maze. It looks like a maze, but it's not solvable because we are actually drawing walls here instead of path. We play a little bit artistically, and what we do here, we have this additional code right here, and this one, of course, we are changing the characters depending on our direction, and also trying to combine current direction with the previous one, so that we're trying to create a little snaky thing. So yeah, let me show you that, how that looks like. So as you can see, we are changing the characters depending how we change direction, and eventually we will fill the entire screen with maze walls. And this example, with this example, we will start our journey in C programming language, because this is what I've done. I started in BASIC, tried to play a little bit, and I want to do something a little bit more faster, so I switched to C. Okay, let's stop that and let's switch to C programming language. Okay, so this is the same as the last example in BASIC, just written in C programming language. Again, we have almost the same variables. This is our lookup table that I explained to you in BASIC, when we had these same values stored as data values. Now we have a simple array, two-dimensional array, and this is just a little bit divided into a couple of functions, nothing special. The whole concept is still the same, and we have these characters for the previous characters, so we create little snaky thing, and that's about it. This is the whole program. So let's run that. Yeah, now that's a difference in speed. And we are done. Okay, so now we will play a little bit more in C programming language and see how can we develop this a little bit more further. Okay, this is the same as the previous one. Again, we are creating the walls. Just a little bit more expand, because once we return from the stack, we're going back through the stack and we continue our path in different directions, so we are splitting the path. So far I haven't dealt with these situations, but now we will also choose a special character for that. I changed the PETSCII character as well, and I just, for each character I defined here, so like a variable, instead of having all those numbers in the code. Everything else is exactly the same as before. Again, yeah, we have additional, instead of just these. So if we progress forward, we choose what was before that snaky thing. Now we also have to decide, when we go through the stack and we find a position where we will split the path and continue in different direction. Now we have to choose which character to select there, so we have to change that character for that position. Yeah, so I have a little bit more peaks here to try to find out which character to use. Not very elegant solution, but again, we are in C, so it's still pretty damn fast. Everything else stays the same. So let me show you that as well. So here we go. So you see, now we have there is no splits in this path, or the walls that we are creating. They are all connected together. That looks pretty nice. Again, this is not solvable maze, because we are drawing walls instead of path. So far I was just coloring differently once we were going back through our stack, so that we have a little bit visual effect. Now I've added a tail, and you can see here this is just a simple very small array of 5 elements. And what we are going to do, instead of just using single color to color our going back through the stack, we are going to add a little bit more effect, like a tail, coloring tail, that's just effect, right? Every time that we are going back through the stack, we are adding a new position to our tail. If we reach the maximum number of elements, we need to shift all the elements, pop out the first element, and we are simply adding new elements at the end of our array. This is what's happening here. And also, position that we are popping out of this tail, we are just coloring that black like we did before. See, when we are going back through our stack, we have a little color tail. Yeah, that's about it. Okay, so this example is the same like we did in BASIC, so that we created actual maze with spaces between the path. And here again I have this little effect with the tail. I have two different characters that I use. Again, this is our lookup table for available directions. So our neighbors, same as in basic example, instead of checking the closest neighbors, we have to check the neighbors that are 2 steps away from us. So this is exactly the same like before. We can check here whether our x and y coordinates are not even numbers, so they are odd numbers. In that case, we remain in the same direction as before, or we can just check that stack counter as well. The same effect is achieved here, so we are remaining on the same direction. If not, we choose some random direction from available ones, and everything else is just the same. You can see that little tail going. There you go. So this is our maze. So in this example, again we are drawing walls, but this time these walls are created to be paths. So we use custom characters that we prepared, and let me show you how this looks like, and then we will go through our code. So here we go. You see, we are drawing a path actually, and we are not taking every second step. We will fill the entire screen with this, and this is my favorite example because it looks fantastic. Visually, it's just beautiful. And we are done. And this is a proper maze. This maze is solvable. There is a path. So yeah, let me show you how we did this. So again, everything stays the same. We're using the same concept. We're using different characters when we move through the screen, depending where we're going, left, right, up and down. Everything is same except the characters that we use, we change them. So these are specially designed characters, and I have a little function here that actually loads the character from the ROM into different location memory, and then change just the characters that we need to change. Everything else stays the same. Yeah, as you can see, we first copy everything from one RAM position that is actually not where we cannot write, we can only read. We copy every PETSCII character to different memory location where we actually can change it, and we just do that. So I have 11 different PETSCII characters that are changed, and I will show you how did I change them in that PETSCII editor. Okay, and here we are in our PETSCII editor, and I will try to draw a maze here. Okay, so this is a little bit of maze. We'll add a little bit here, something. Okay, and we'll add this one here. And okay, you can see these are the balls. Now let me apply a special set of characters. You see how that looks now, completely different. Also, I didn't change those pluses, so let's go change those. And special characters, this one, where is plus. So you can see this, how this original character looked like, how does it look now. So what I did actually with this is changing the character that looks like a wall to look like a path with a little bit of wall on the borders. So this blue here represents wall, this here also represents wall, and this big area, light area here represents a path. So yeah, and I need to change the plus as well now. And plus should be something like this, so it's filled everywhere except for the corners. Oops, here we go. This is our new plus sign. You can see how that looks like. If I go back to our screen, you can see now how it's that everything is filled. I did make a mistake with this, missed something. Yeah, of course, here as well. Oh bloody hell. So I'm here, look, this one is good, this one is okay. You see how that looks like. So between these two characters there is a wall. This blue line, thin line, represents our wall. So yeah, that's how that maze is created. Okay, and we are done with this type of algorithm. We are going to take a look at another algorithm today, and it's called Recursive Division. And I didn't implement that in BASIC because it actually requires recursion. I only implement that in C programming language. The whole algorithm is very fast, and there is even less code than for these examples. So this is our implementation of recursive division algorithm in C. As you can see here, it's very similar approach. We define our walls, our sides of each position with the same method. So we're using 4 significant bits in a byte to define each of the sides, but actually we don't need all of them. So that's the beauty of this algorithm, or this implementation that I've done. So we have our grid. This is the size of our maze, so it's going to be 25 columns, 25 rows, and this is our lookup table for characters. So as you can see, this is how I implemented this. So we are actually going to use only 4 different characters. The first one is 32, which is space, that's completely empty. The second one is 111, so let me show you which one is 111. Is this one. So we only have bottom border, that's the one, and then 103 is going to be, it should be this one right here, only right border, that's it. And we have just one more combination, one more character, and that's this one, 122, this one right here. So combination of right and bottom border together, that's it. So 4 different characters, or 3 different PETSCII characters plus empty space, like everything is empty. So that's all we need to create this maze. And we are beginning with filling our entire maze, entire grid, with all position having both of those borders activated. So every position has both of the sides closed, and that's this character right here. So if I try to fill it, so we're starting in this position, and then we call this function that is draw maze. So this function just pokes every position on the screen. So what we will see is that grid fully closed. That's it. And then we starting with calling this function, which is called divide, starting from 0, 0, that means top left corner, and full complete width and height, that means full area that we want to cover in maze. We're starting with that, and after that we are going to redraw the maze again. Now this time our positions will have different values, and again in the end we are just waiting for some key to be pressed that we exit the program. So that means that just maze is staying on the screen until we do something. So the whole work is done by this divide function, and here it is. So you can see that this just x and y coordinate of top left corner and x and y coordinates of bottom right corner. That's about it. Here we calculate the difference between them so that we can define orientation of our area. Is it horizontal or vertical? So that we can choose whether or not to divide this horizontally or vertically. So this section here is activated once we reach any kind of area that is that has only one column or only one row, and in that case we are just opening. If we go horizontally, then we opening this side. If we going vertically, we opening bottom side. So we are actually creating a tunnel. That's about it. Most of the time what we are doing is defining whether or not we are going to split our area horizontally or vertically, or in case that area is has equal sides, then we just randomly pick one of those two, and then we select random position in that area, random x and y coordinates. Of course we calculate the absolute position of this, and then if we go horizontally, in this case we are removing this bottom side. We are opening wall through this area. So yeah, we have to go through south, and in case that we are making a vertical division, so we are dividing vertically, then we have to remove the east wall so that we have pass through. And these pokes here are just they're not necessary. They're here just to animate a little bit, to make it more interesting. Once we divide this area, what we have now is two different areas, and then we recursively call again the same function for each of these areas. And this is the entire code. This is it. There is not, look, nothing. There is no code at all. So this is the beauty of this algorithm. It's very simple, but it's very powerful. Let me run this code and show you how this looks like. See? We started with full grid, and now the paths are created through this grid, through these walls. And if we take a look this upper left corner, there is a path 100% from the top left corner to the bottom right corner, and also vice versa. So simple concept, but so powerful. And by using this little pokes that I added, and makes everything a little bit more slower, of course. It's a little bit more interesting to watch, but if I remove that, the speed is incredible. I mean, it's absolutely incredible how fast it generates maze. So yeah, I will show you one more example of this same code. Just this time we are going to again use custom PETSCII characters. These are our custom characters. Of course we don't use all of them. I just borrowed this from previous algorithm, but Again, we don't use all of those special characters. We use just 3 of those. What I want to do is increase the height and width. So let's go with 25 and yeah, 40. So width is going to be 40, height is going to be 25. Here we go. This is our maze. And it's absolutely beautiful. Okay, so yeah, this is all that I have for you today. I hope that you enjoyed this little trip through the mazes. Until next time, goodbye.